Welcome to Chapter 9, Hypothesis Testing. This is an introduction to hypothesis testing, and we're also going to cover the P-value approach, which is one of the two ways that you can do a hypothesis test. Now in this video we're going to cover the null and the alternate hypotheses. The only test statistic we're going to get into is the one for when you want to test a population mean when you know the value of sigma, sigma being the population standard deviation. Later on we're going to cover one that's just referred to as applications, when we'll cover all three of these with different problems. But here what I want to do to introduce you to hypothesis testing is to connect Chapter 8 to Chapter 9. Chapter 8 dealt with interval estimation, and I want to use that as kind of a bridge to get over into Chapter 9. Now in hypothesis testing, we have the value of a parameter in a population that we're testing. We're testing a statement about that particular value. The null hypothesis is what you're accepting as being true when you do the hypothesis test. The alternative hypothesis, which you have the H with a subscript of A, the A just means for the alternative, is what you're really trying to show. And it's going to be the opposite of what's stated in the null hypothesis. The null hypothesis, you have an H with a subscript of 0. Now the hypothesis testing procedure is taking data from the sample to test the null and decide whether or not you're going to be able to reject it or not reject it. If you reject the null, then you're going with the alternative hypothesis. Sometimes it's called the alternate hypothesis. Now rule number 0 of hypothesis testing is that you always put equal to in the null hypothesis. It never belongs in the alternate hypothesis. Now there are two types of one-tail test, and then there's also a two-tail test. The one-tail version could be when you're looking to show that the parameter that you're testing is smaller than a certain value. Another one-tail case is when you're trying to show that the parameter that you're testing is larger than a value. Now here we're testing the mean. So we're using a subscript of 0 on the symbol mu to represent the value against which we're comparing. In the two-tail form of the hypothesis test, the alternate or the alternative hypothesis is you're saying it's just not equal to that value. But in all of these situations, you always put the equal part up in the null. In the two-tail case, the alternate says it's not equal to that value, so under the null you assume it is. In the one-tail case, for the upper tail, or the greater than situation, we're trying to show that the value of the parameter is larger than what's hypothesized. But up in the null, you're saying it's less than or equal. But when you do the test, you're going to use that value. Same thing for the one-tail version for a lower tail. We're trying to show that the mean of the population is smaller than this particular value. Under the null, we assume it's greater than or equal to. But logically, it's got to be one way or the other. But the null and the alternative, or the alternate hypothesis, they're pretty much going to be opposite of each other. Now to introduce the topic of hypothesis testing, I want to build a bridge between Chapter 8 and Chapter 9. This was a problem that we had in Chapter 8 when we're trying to estimate the value of the mean. We had a problem here to where we had sample information. We knew what the value was for x bar, for the mean of the sample. We knew what the population standard deviation was, and we wanted to come up with a confidence interval estimate of the mean. Now when you have an interval estimate, you don't have a value for the mean. When you have a hypothesis test, you do have a value for the mean. But the purpose behind interval estimation is to come up with an estimate for that population parameter. But what you come up with is a lower bound and an upper bound, and a level of confidence that says that it's somewhere in that range. But when you're doing an interval estimate, you take the value of the sample statistic and then you add and subtract the margin of error. Now, in this particular problem, we were trying to get the 95% confidence level, or we had a 0.95 value for our confidence coefficient, and we could use that number and figure out that the z-value is going to be 1.96. Then we can take and figure out the standard error of the mean, which was the 4,500 divided by the square root of 36. Now, when you multiply the z-value times the standard error, you come up with the margin of error. So for this problem, it was 1,470. Now, the 95% confidence interval estimate, we're going to take the value of the sample mean, and then we're going to add and subtract the margin of error. So when we finish doing the arithmetic, we come up with the lower bound being 39,630, and the upper bound is being 42,570. So we are 95% confident that that interval contains the mean of the population. We don't know what the mean is. Now suppose that we were doing a hypothesis test with two tails. Under the null, we assume a value for the mean. And what we can do if it's a two-tailed test is we can take this interval estimate and then we can look and see whether or not that value is contained in the interval. Under the null, we're assuming a certain value. Now if that value is inside the interval, then we have to accept the null. But if it's so far away that it's not contained within the interval, then it's not really very likely, based on the sample, that that's the correct value of the population mean. But you can set up a two-tailed hypothesis test to be equivalent to a confidence interval estimate. You just have to have the same level of confidence that corresponds to the level of significance that's in your hypothesis test. The relationship between the level of significance and the confidence coefficient is that they're complements. If you have a 95% confidence interval estimate, that corresponds to having a 5% level of significance. Now I'm taking the same scenario and I'm rewording the problem a little bit to make it a hypothesis test. Now Discount Sounds thinks that the mean annual income of the individuals in the marketing area for this new location is $40,000. So we have a value that we're testing as the value for the population parameter for the mean. The question is, at the 0.05 level of significance, is the evidence provided by the sample strong enough for them to conclude that the mean annual income differs from $40,000? This is a two-tail test. We're trying to show that the mean differs. Now we're doing this at the 0.05, so it's equivalent to a 95% interval estimate. Now the 95% interval estimate that we came up with was from 39,630 to 42,570. Because the null, the value of the mean under the null is 40,000, and it's contained within that interval. It's between 39,630 and 42,570. We're going to accept the null hypothesis. If the 40,000 value had been outside of the interval, then that's the same thing as rejecting the null hypothesis. But for a confidence interval estimate to be equivalent to the hypothesis test, you're going to have a two-tailed version, and the value of alpha is going to have to be 1 minus whatever your confidence coefficient is. even though there's a relationship between the confidence interval estimate and hypothesis test, I want you to understand a hypothesis test as, it's really a different type of problem. You have a value and you're trying to test against that value. Now in this problem we have a two-tailed case. The value that we're assuming under the null is 40,000. So in that population we're assuming that that mean is really 40,000. And everything that you do in a hypothesis test, it logically flows from that assumption. Now, under the dictates of the problem, the value of the standard deviation in the population was 4,500. So that lets us use a certain test statistic. The sample statistics, we found a value in the mean of 41,100, and the sample size for that particular problem was 36. Now, the question that you're really answering when you do a hypothesis test is that number, is that 41,100, is that so far away from 40,000 so that it's not believable that that 40,000 is correct? One can ask the question, is x bar equal 41,100 significantly far away from the hypothesized value of $40,000? Well, whether or not it's significantly far away depends on that level of significance. Now it turns out there are two ways to do a hypothesis test. One of them is based on what's called the P-value approach, and that's what we're going to be talking about in this presentation. And then in the next presentation we're going to look at the critical value approach. But what you need is a formula so that you can take the statistical information, those calculations that you do in the sample, and answer the question. And the formula is referred to as a test statistic. But you can take the sample information. In this case we have the x bar value and we have the sample size, the 36, and we'll plug those into the appropriate formula, and then we should be able to figure out the p-value, and then we'll address the critical value approach. We'll address that later. Now these formulas should look familiar. We came up with these formulas, this one back in chapter 7. We also made use of it in the slightly different form in chapter 8. But if you're testing the population mean and you know sigma, then you can just convert it to the standard normal by taking the statistic, you subtract the mean of that statistic, you divide by the standard deviation of that statistic, or what's referred to as the standard error, and then you get your z-value. Now the p-value is a probability. The value is based on the test statistic. The way that you calculate it depends upon the type of hypothesis test, whether it's a lower tail test, an upper tail test, or a two-tail test. But the way that you use it, it's always the same. You calculate it differently based upon what type of test it is, but you always use it the same way. You can kind of think of the probability for the p-value as being the likelihood that the null hypothesis is true. Probability values have to run between 0 and 1. Now the closer that that p-value is to 1, the more likely that the null hypothesis is true. The closer that that p-value is to 0, the more likely that the alternate or the alternative hypothesis is true. But the rule is that you reject the null if the p-value is less than or equal to alpha. Alpha is called the level of significance. It's the complement of the confidence level. If you're 95% confident, then you have a 0.05 level of significance. Now when I teach hypothesis testing in the classroom, I always like to put this little representation up on the board. I'll draw the null and I'll draw the alternative hypothesis, But instead of putting them right next door to each other, I'll move the level of significance in between the two. We're going to compare the p-value to alpha. The p-value is a probability. Alpha is a probability. So you can compare those two directly to each other. Now, probabilities have to be between 0 and 1. As long as that p-value is above alpha, then you're not going to reject the null. Large p-values support the null hypothesis. As the p-value gets smaller and smaller and smaller, eventually it's sufficient to go with the alternate. You have to prove the alternate. If you're not able to prove the alternative hypothesis, then you have to fall back on the null. The null is what you're willing to accept without proof. Now in this case, we're trying to show that the mean annual income differs from $40,000. So the alternative hypothesis is that mu, the mean, is not equal to 40,000. If we get a small enough p-value, if it hits 5%, or if it gets below 5%, then we're going to reject the null. Otherwise, we're not going to reject the null. Now this slide shows relationships between the value of the p-value and what it means in terms of the hypothesis test. If it's really small, if it's less than 0.01, then you have really, really strong evidence to go with that alternate hypothesis. When that p-value, when it's between 1% and 5%, then you have fairly strong evidence that the alternate is where you need to go. If it's between 5% and 10%, well, it kind of weakly suggests that the alternate is what you should go with. But anything that's above 10%, you need to go with the null. You just don't have enough evidence to prove the alternate. Now we're going to take the statement of the problem and use the information that we have, and we're going to calculate the test statistic. You plug in the value for x bar, the 41,100. You plug in the value hypothesized. That's the mu with the subscript of 0. So we plug that 40,000 in for that. The 4,500 was the population standard deviation, and 36 was the sample size. Now we go through the arithmetic and we come up with 1.47. Now this number was rounded off to 2 decimal places. Usually that's enough for a z-value. But the 1.47 is called the computed value of the test statistic. You take the sample information, you plug it into the formula, and you compute the test statistic. Now it's this value that we're going to use to come up with the p-value. Now when you have a lower tail test, when you're trying to show that the value of the parameter is less than some number, you want to take the probability that you're less than or equal to the computed value. Now we can look up the value 1.47 in the z-table. And the z-table is going to give us the probability that you're less than or equal to that value. So if you look up 1.47 in the z-table, you're going to get 0.9292. But we're not doing a lower tail test. Now anytime you have an upper tail test, when you're trying to show that the value of the parameter is larger than some number, what you're going to do there is to find the probability that you're greater than or equal to the computed value. Now the 1.47, when you look it up in the z-table, you're going to get the probability to the left of it. But if you're doing an upper tail test, you want the probability to the right of it. So you take 1 minus the probability that's to the left of it. And that'll give you the p-value for the upper tail test. But we're not doing an upper tail test. Now when you have a two-tail test, What you do there is you double the smaller of the two p-values. There's a p-value for a lower tail test. It's to the left of the computed value. There's a p-value for the upper tail test. It's to the right of the computed value. Take whichever one of those numbers is smaller and double it, and that's going to give you the p-value for a two-tail test. Finally, we do have a two-tail test. We're checking equal 40,000, and the alternative is not equal to 40,000. Our level of significance was 0.05. Now, if it had been a lower tail test, we would have come up with 0.9292. If it had been an upper tail test, we would have come up with 0.0708. But since it's a two-tail test, you take 2 times the smaller of the two. So 2 times 0.0708 is 0.1416. But I've tried to show in green where the p-value is for the two-tail test. Now, because that p-value, the 0.1416, is greater than alpha, the 0.05, we do not reject the null hypothesis. Under the null, we were assuming that the mean was 40,000. The alternative, or the alternate hypothesis, we were trying to show that the mean differs from 40,000. We did not reject the null. So at the 0.05 level of significance, we have insufficient evidence. We don't have enough evidence to conclude that the mean annual income differs from $40,000. And that's the conclusion of the hypothesis test. Now, this concludes this little introduction to hypothesis testing. We've introduced some new terminology. We've introduced the concept of the p-value. Just to kind of summarize what the p-value is. If you have a lower tail test, the p-value is the probability to the left of the computed value. If you have an upper tail test, the p-value is the probability to the right of the computed value. If you have a two-tail test, you double whichever one's smaller. If you doubled the larger one, chances are you're going to get a number bigger than 1. And that's not possible for a probability value. Now, the next presentation, as part of Chapter 9, is going to introduce you to the critical value approach. And then the last one, we're going to deal with the different test statistics. We have one case where we're testing the mean and we know sigma, which we were using here. We're going to have another case where we're testing the mean and we don't know sigma, and we're going to use the t-distribution for that. And then the third case is when you're dealing with qualitative data and you're testing using the proportion. But we'll get to those in just a little bit.